Continuing on physical chemistry, we are starting chapter 10 now. We are in section 1. We're going to talk about activities and activity coefficients. Now, if we have only non-electrolytes, an ideal solution is the chemical potential of substance I for an ideal solution. That's equal to chemical potential of the substance I in the standard state plus R times the absolute temperature times the natural log of the mole fraction of the substance I. ID is for ideal, obviously. Now we're going to solve for the mole fraction of the substance I. So we get that chi I is equal to E to all this exponent. Chemical potential of the substance I in the ideal solution minus the chemical potential of the substance I in the standard state divided by RT. Now remember, this is for non-electrolytes only, and this is assuming that we're in an ideal or an ideally dilute solution. Now we're going to define the activity A sub I as this: E to the chemical potential I, notice there's no ideal, minus the chemical potential I in the standard state divided by RT. So this is just like mole fraction, but is for a real solution. Now what we're going to do is solve for the chemical potential of the substance I. This is in an actual solution, a real solution. So we're going to take the natural log of both sides. We get the natural log of the substance of the activity of the substance I, and that's equal to the chemical potential of the substance I minus the chemical potential of the substance I in the standard state divided by RT. And then let's see, we just do some algebra to move around, and we end up the chemical potential of the substance I is equal to the chemical potential I in the standard state plus RT times the natural log of the activity of the substance I. And this is actually for a real solution, or any solution. It'll still work with ideal and ideally dilute solutions. So it's the same formula, just that the activity of the substance I replaces the mole fraction of the substance I. Now compare that, we had chemical potential, or we have the chemical potential of the substance I is equal to the chemical potential I in the standard state plus RT times the natural log of the activity of the substance I with the chemical potential I in an ideally dilute solution, or our ideal solution, and that's equal to chemical potential I in the standard state plus RT times the natural log of the mole fraction. So like I said, if you have an ideal or an ideally dilute solution, the mole fraction I will be equal to the activity I. Now when the chemical potential of the substance I is equal to the chemical potential of the standard state, then the activity of the substance I is going to be equal to the activity of the substance I in the standard state, which is equal to 1. And therefore, RT times the natural log of the activity of the substance I is going to be equal to 0, because the natural log of 1 is equal to 0. Now remember, the chemical potential I is going to be a real solution. Chemical potential of substance I, ID, superscript ID, that means ideal solution from now on. Make sure you keep track of which is which. So what happens if you subtract them? Then the chemical potential of the substance I minus the chemical potential of the substance I in ideal, in other words, the difference between the two, that's going to be equal to RT times the natural log of the activity minus RT times the natural log of the mole fraction. And then you combine those by dividing. So you get RT times the natural log of the activity divided by the mole fraction of the solute. So we say this fraction, the activity of the solute divided by the mole fraction of the solute, is the departure from ideal behavior. Now we're going to define another. This is a gamma of substance I. So gamma, remember, 3 equal sign means equal, always equal to, or defined as. So gamma of I, that's equal to the activity of I divided by mole fraction of I. And that's the little gamma. So gamma I is the activity coefficient of I. Not to be confused with activity. A was activity, gamma is activity coefficient. So we can solve for activity by getting the activity of I is equal to the gamma I times chi I. So activity is equal to activity coefficient times mole fraction. Now, gamma of the solute is equal to 1 for non-electrolytes in an ideal or ideally dilute solution. When the gamma of the solute is equal to 1, then the activity of the solute is equal to the mole fraction of the solute. Now, activity of I is greater than 0, and the activity coefficient is greater than 0. The activity and the activity coefficient, they have no units, they have no dimensions. The activity of I is a measure of the chemical potential I in the solution. As the chemical potential increases, then its activity will increase too. That's the end of chapter 10, section 1.